In the previous lecture, we have started to deal with the problem of tight binding approximation. And in the first part of the lecture on this tight binding approximation, you have seen the concept of how energy bands are formed in a solid. But our discussion in first lecture on this tight binding approximation was only qualitative. It means we have not made any calculation to find the bandwidth or how this energy band is formed. But we have analyzed the problem in qualitative manner. In fact, as I have told you in the first part of the lecture, that this problem was first of all solved by Bloch, and this tight binding approximation is also known as linear combination of atomic orbitals, that is LCAO. Because in this linear, why it is called linear combination of atomic orbitals, we have learnt in our first lecture that actually when the atoms are far separated and then the wave functions of the atoms do not overlap, and the electron of each atom has discrete energy levels. Okay, but when the atoms are moved close and a solid is formed, then there is an appreciable overlapping of wave functions of the atoms. And we have seen if there are n atoms whose wave functions get overlapped, then what happens? Then you have seen that each energy level of an isolated atom is splitted into the energy levels whose number is equal to the total number of atoms. It means if there are n atoms and wave functions of all these n atoms are overlapping, then one energy level of an isolated atom is splitted into n energy levels, and the spacing between those energy levels is so small that they actually forms a continuous band, and that is called energy band. So in this way we have analyzed this problem in our first part of the lecture. But today in this second part of the lecture we are going to analyze the problem in quantitative manner, and we will actually calculate the width of the bands in different type of crystals. Okay, so let us try to find the bandwidth and energy calculation and how this band is formed in a quantitative manner. And for simplicity we will do this tight binding approximation for the band of energy formed by s electron states, only s electron states. In fact, for this we consider the ground state wave function of an electron moving in a potential V naught R. Actually this V naught R is the potential when when the electron is free, or you can say there is no overlapping of atoms. Okay, or you can say that this is potential of an isolated atom, and in that condition the wave function of the electron is psi naught R. Okay, and its energy we assume is E naught. So if you consider the ground state wave function of an electron moving in a potential V naught R of an isolated atom, and this psi naught R is its wave function and its energy is E naught, then this wave function will satisfy the Schrodinger equation which I have written here in this equation 1. So this del square psi naught R plus 2m over h bar square times E naught minus V naught of R psi naught of R equal to 0. This is the wave equation, or you can say the time independent Schrodinger equation for S state of the electron. Okay. Here, for simplicity, we also consider that this wave function psi naught of R is non-degenerate. When you say that this psi naught R is non-degenerate, what does it mean? It means it is the only function corresponding to the energy E naught. It means the corresponding to the energy eigenvalue E naught, there is one and only one eigenfunction, and that is psi naught R. And so this function is non-degenerate. Okay. And this is possible in case of S electron, Okay. Actually, with this assumption, the treatment will be applicable to S levels only, and it will be shown later on that S levels correspond to S bands. Okay. In fact, the treatment of degenerate P, D, F, E and so on levels into the P, D, so on bands are more complicated. It means if you talk about the band formation of this P level, which is actually degenerate, you consider the band formation for the D levels, which is also degenerate, then this problem will become very complicated. And in this lecture, I am not talking about the formation of P band and D band. Our discussion will be limited only just for the formation of S band from the superposition of the S energy levels. Okay. And so we will left the discussion on this more complicated problem of formation of P and D band. Okay. Now let us suppose that there is a large number of similar atoms, as you can in this figure. I have assumed a large number of similar atoms, and these atoms was initially isolated, but now let us consider that they are brought together in the form of a crystal, as you can see in this figure. Okay. Now let us take a particular atom, you can see it here, as an origin, or you may say that this particular atom is situated at the origin of our coordinate system. Okay. And then we consider any atom, say the jth atom, whose position vector I have shown with respect to this arbitrary origin is Rj. Okay. And this Rj may be represented, this Rj is the lattice vector, actually, you can say. Now, in view of the assumption that the motion of the electron in the vicinity of a particular atom is only slightly influenced by the presence of other atoms, the electron wave function near this jth atom is approximately independent of the other atoms and is approximately given by psi naught of R minus Rj. Okay. So if you consider that there is an atom here whose position vector with respect to this jth atom is R minus Rj, then the wave function of this electron will be almost given by psi naught of R minus Rj, provided that this another atom is in the vicinity of this jth atom. Okay. Now, once you know the wave function of an electron situated near this jth atom, then by summing over or you can say then by taking the linear combination of wave functions like psi naught of r minus rj, you can get the crystal wave function for the electron, and that can be written in this manner. You can see. So I have written that crystalline wave function may be constructed by superposing the atomic wave functions or by taking the linear combination of atomic wave function or atomic orbitals in this way. This psi of r, this represents actually the crystalline wave function, and that is, you can see, is simply the linear combination of wave functions like this psi naught r minus rj. And so psi of r is given as summation over j from 1 to n cj times psi naught of r minus rj. Actually here n is the total number of lattice ions. So summation is done here from 1 to the total number of lattice ions. And psi naught, you have seen, this is atomic S state wave function. Okay? Or you can say that this is wave function for a free electron, okay, in s orbital. And rj is the position vector of an jth atom. Okay. Actually, as you know, this expression satisfies the approximation that if r lies close to rj, all contributions in the sum will be small, except that from this function psi naught of r minus rj, all the contribution from other atoms are neglected. Okay? However, since we are dealing with an electron in a periodic potential, so the wave function must be Bloch function, because we have learnt earlier that whenever an electron moves in a periodically varying potential, the wave function of the electron is a Bloch function. And here we have considered that our electron is moving inside a crystal, and you know inside a crystal the potential varies periodically. So definitely this function psi of r must be recognized as a Bloch function. And if psi of r will be recognized as a Bloch function, can you say what should be this Cj? Then this Cj must be a plane wave. So you can see Cj can be written as e to the power I k dot rj. Okay. So I have mentioned it here. You can see that as the electron is moving in a periodic potential, the wave function must be a Bloch function, and the coefficient Cj must describe a progressive wave within a crystal, and so Cj is equal to e to the power ik dot rj. Okay. And so now, in the light of this value of Cj, you can write this equation 2 in this manner. Psi of r equal to summation over j 1 to n e to the power iota k dot rj times psi naught r minus rj. Okay. Actually, this function 3, which is actually the Bloch function, and this is actually the solution of the Schrodinger equation for the entire crystal. Okay. So if you will now write the Schrodinger equation for the entire crystal, what will be that time independent Schrodinger equation? Actually, the Schrodinger equation for the entire crystal can be written like this. This is del square psi of r plus 2m over h bar square e minus v of r times psi of r equal to 0. Actually here, this psi of r is the wave function of the electron wave when the atoms are not isolated, but they have aggregated to form a solid. form a crystal, and E is then energy of the electron inside the crystal, not isolated in isolated atom. Okay, and this function psi is actually the solution of this Schrodinger equation defined in equation 4. Okay, here this V of R is the crystal periodic function, crystal periodic potential function. So you can see in our discussion we have encountered two potentials. First of all, you have written Schrodinger equation for a free electron, or you can say the electron in s orbital of an isolated atom, and that equation has been written in this equation 1. And so this V naught of R, this is called atomic periodic potential. This is atomic periodic potential, and V of R in this equation, this is called crystal periodic potential function. And how this these two potential functions, that is V naught of R, which represents the atomic periodic potential function, and V of R, which represents actually the crystal periodic potential function, how these potentials vary with distance r, you can now see. Actually here I have plotted a graph between potential function V in against of r, and you can see this full line curve actually represents the variation of crystal potential. Okay, this full line curve. But this dotted line curve, you can see this represents the variation of the atomic potential, atomic periodic potential. Okay. Now, after writing the Schrodinger time independent equation for an electron inside a crystal, okay, now you can define this energy eigenvalue of the electron. Okay, actually, you know, this energy eigenvalue will be simply the expectation value of the Hamiltonian. Okay, you have definitely studied the postulate of quantum mechanics, and if you have not studied, you can look my playlist of quantum mechanics, where you will get a detailed explanation, a detailed description of the expectation value of quantum mechanical operators. And then you can see the energy eigenvalue of an electron in the crystal are approximately given by this. E equal to, this is actually psi h psi over a scalar product of psi with psi. This is in bra and ket notation, and in integral form this is written as integral psi star h psi d tau over integral psi star psi d tau. Here d tau, you know, this is elementary volume. Okay. Now here H is the crystal Hamiltonian. Okay. H naught, when you will write H naught, this will be actually the free electron Hamiltonian, but H is crystal Hamiltonian. It means this is Hamiltonian for the electron inside the crystal. Mark it. And you know, this Hamiltonian will be given like this. This is minus h bar square over 2m del square plus V of r. Okay. Now here we apply a simple algebra. Actually, our aim is now to introduce a perturbation potential term in this expression, and for this we simply add a term V naught R of R minus Rj, and we also subtract the same term V naught of R minus Rj. So the result remains same. Okay. But now let us consider the sum of these first two potentials, that is V of R minus V naught of R minus Rj. Let us take it as V dashed of R minus Rj. Okay. So finally, the crystal Hamiltonian H is given like this. This is minus H bar square over 2m del square plus V dashed of R minus Rj plus V naught of R minus Rj. Actually, this what is this V naught? Sorry, what is this V dashed of R minus Rj? You can see this V dashed of R minus Rj. This has been written at the place of what? This is equal to V of R minus V naught of R minus Rj. So actually, this V dashed of R minus Rj actually represents the potential energy of the electron in the crystal at a point R, whose position vector is R, okay, minus the potential energy of the electron at the same point R, where there is only a single atom, namely located at Rj. That is, this is V of R, which is actually the potential energy of electron at the point R, and minus this much. Okay. So, in other words, you can say that actually this V dashed of R minus Rj represents the potential energy of the electron at the point R, resulting from the presence of all atoms except one located at R equal to Rj. Okay. Further, you can take the assumption in your mind that the greatest contribution to the potential energy arises from the parent ion. Here this jth ion, as you can see, this is the main source of potential. So our assumption is that the main source of this potential is in fact the parent ion, and which I have taken as an jth ion. And so we can conclude that it is a small negative quantity or a small perturbation on the atomic potential V naught of R minus Rj. So in nutshell, you can say, what is this V dashed of R minus Rj? You can say that this is simply a small perturbation on this atomic potential V naught of R minus Rj. So when the atoms get aggregated and solid is formed, then the atomic potential is perturbed by this potential V dashed of R minus Rj. And so that the Hamiltonian for the crystal is different from that of the free electron or the atomic Hamiltonian. If you talk about atomic Hamiltonian, then this perturbation potential term will not remain here. Okay. Now, let us see. So now, in this expression or for the expectation value of E, in denominator there is a scalar product of psi with psi. And if you consider that this atomic wave functions are normalized, then what will be this scalar product? This scalar product, you know, is in integral form. It is given like this. This is integral of psi star psi d tau. And as the total number of ions is n, so according to the normalization condition, this integral will be equal to n. So psi star times psi d tau, integral of this much, is equal to n. So assuming that the atomic wave functions are normalized, we can write this integral equal to n. Okay. Now we will make the use of this value of the denominator in this equation, that is equation number 5, okay, and we will also use equation 6 and 8 in equation 5. This is your equation 6. This is the how the Hamiltonian of the crystal is defined. You can get from this equation 6 at the place of h, and at the place of this integral or the scalar product of psi with psi, you get n. So we will use this expression for Hamiltonian, which has been defined in equation 6, and this equation 8 in equation 5 to get the energy eigenvalue of the electron. Okay, and so you can see this energy eigenvalue E will be equal to what? After substituting all those values, you will see that this is 1 over n summation over j summation over L e to the power iota k dot rj minus rl times integral psi naught star r minus rl times, now this is at the place of the Hamiltonian h, this is minus h bar square over 2m del square plus v dash of r minus rj plus v naught of r minus rj, and this is operated on psi naught of r minus rj theta. Okay, this 1 over n has been written for the denominator. Okay, now you can see that if we talk about the atomic Schrodinger equation, when the electron is present in atoms, in isolated atoms, then actually the Schrodinger equation will be given by H naught psi naught equal to E naught psi naught. Here H naught is the atomic Hamiltonian, mark it. Psi naught, we have seen this is atomic eigenfunction, okay, and E naught is the energy of our electron when the atoms are isolated. E is its energy when the electron is in the atom inside a crystal, but E naught is the energy of electron when the atoms are isolated. Okay, so this is the difference. Now this H naught, which is atomic Hamiltonian, that can be written like this. This is minus h bar square over 2m del square plus v naught of r minus rj, as I have told you here, that actually this is the perturbation term, perturbation potential. But if the atoms are isolated, then there will be no perturbing potential. And so the free atom Hamiltonian is equal to this much. And that is operated on psi naught of r minus rj, and E naught times psi naught of r minus rj. So I have written here, you can see E naught, energy of electron in an isolated atom. Okay. So if you have defined this expression equal to E naught psi naught of r minus rj, then this equation 9 using that result can be written like this: E equal to 1 over n summation over j summation over L e to the power iota k dot rj minus rl integral psi naught star r of r minus rj times E naught plus v dash of r minus rj times psi naught of r minus rj theta. You can see this has been obtained by the use of this result on this equation 9. Okay. Now we will simplify the RHS of this equation 10 considering the different terms. And in this regard, first of all, let us consider the term containing E naught. in RHS you can see we have to consider the term which contains E naught. You can see the term which contains E naught is given like this. This is 1 over n summation over j summation over L e to the power iota k dot rj minus rl times integral of psi naught star of r minus rl e naught psi naught of r minus rj d tau. This is the term which contains E naught. Okay. Now, we are actually considering a small overlapping case or weak perturbation. So, if the overlapping is small, in that condition, we may neglect in the summation over L all terms except L equal to J. Okay? And when you will neglect the all terms except L equal to J in the summation over L, then what will be the term containing this E naught? After that assumption that we will neglect all the terms, all that we will neglect in the summation over L, all the terms except L equal to J. Why we will actually neglect those? Because we are considering that the overlapping is small and so there will be weak perturbation. And in that condition, the term containing E naught, you can see here, in that condition, this term will become like this. This is 1 over n summation over j psi naught star of r minus rj E naught psi naught r minus rj d tau. Actually, this integral represents the energy eigenvalue multiplied by the total number of ions. So, the value of this integral is n times E naught, and divided by n. So, this n and n will cancel out and you will get E naught. Okay? Actually, this is just the definition of the eigenvalue, the expectation value of energy E naught. Okay? So, from this we have seen that this expression is equal to E naught. Okay? Now, we will consider the term containing the perturbation potential V dashed of R minus Rj. And see this expression, equation number 10. In equation 10, you have to select now the term containing the perturbation potential V dashed of R minus Rj. And you can see this expression, that term will be equal to what? That term will be 1 over n summation over j e to the summation over L e to the power iota k dot rj minus rl integral psi naught star of r minus rl times V of r minus V naught of r minus rj times psi naught of r minus rj d tau. So, this is the term containing the perturbation potential, this V dashed of r minus rj. Okay? Now, since all the terms in the summation over j are identical, we need consider only one term for which j will be equal to 0 and multiply this result by n. After multiplication by n, what will be this equation 13? You can see this will be n times 1 over n summation over L e to the power I k dot RL. Actually, I have actually told you that because of the similarity of all the terms in the summation over J, because of the periodicity of the lattice potential, we need to consider only one term, say for simplicity that for which J equal to 0, and we multiply this result by n. And after doing this algebra, you can write this equation 13 in this manner. This is n times 1 over n summation over L e to the power minus ik dot RL integral psi naught star of R minus RL times V of R minus V naught of R times psi naught of R d tau. Okay. Actually, the magnitude of this integral defined in this equation 14. The magnitude of this integral depends essentially on the extent of overlap between the two wave functions centered on the atoms separated by a distance RL. Separated by a distance RL. Okay. Where L refers to all atoms of the crystal, and therefore their actual evaluation is quite tedious. However, in view of the fact that the wave function psi naught falls off very rapidly with distance, the contributions of the terms in the summation decrease very rapidly as RL increases. And it is therefore a reasonable approximation to consider the nearest neighbor terms only. Okay? And so that we shall neglect all the terms beyond the nearest neighbor one in this equation 14, and further we assume that the functions psi naught are spherically symmetric. Okay? And all nearest neighbor contributions will be same, because we consider that psi naught is spherically symmetric, and so you can consider that the contribution of all nearest neighbor will be same. And actually this is the case for the non-degenerate electrons, and our treatment will thus become applicable only to the cases where the ground state electronic configuration in the free atom corresponds to an S state. Okay. For example, you can take alkali metals where this approximation will be applied. Okay. Now, actually, to get the value of bandwidth and energy of electron in an atom inside the crystal, let us now introduce two parameters. Okay. The first parameter we denote by the symbol alpha, and the another parameter by the symbol gamma. And how these two parameters are defined, let us see. So this is just definition. Equation 15 is the definition of alpha and 16 is the definition of gamma. And so you must remember it, because these two parameters has been defined in this manner. Alpha is defined as minus integral of psi naught star of R times V of R minus V naught of R psi naught R d tau. Okay? And this gamma is defined by minus integral of psi naught star R minus RL V of R minus V naught of R psi naught of R d tau. Okay? Actually, here this vector RL connects the atom at the origin with the nearest neighbor atom L. You can see this is, if you consider that this is a Lth atom and this is the position vector RL and this is the origin. Okay? So RL connects the atom at the origin with the nearest neighbor atom at L. Okay? And in the light of these two equations, 15 and 16, now you can write this equation 14 in terms of alpha and gamma. This will be given like this. Here this n and n will actually cancel out, and there will be C for minus integral of this much. We will write what? We will write alpha. So this will be minus alpha. And for the remaining terms, for this we will write minus gamma times summation over L e to the power minus ik dot RL. Okay. So now this equation 14 has been written in terms of these two arbitrary parameters alpha and gamma defined in equation 50 and 60. Okay. Now, if your aim is to find the energy of the electron in an atom inside the crystal lattice, then you should combine this equation 17 with equation 12. See the equation number 12. Okay, this equation 12. And then we will obtain for the energy eigenvalue which is defined in this equation 10. So what will be then E? You can see, making the appropriate algebra, E will be then given by E naught minus alpha minus gamma times summation over L e to the power minus iota k dot Rn. This is actually our final result. And in this equation, E is energy of the electron in an atom inside a crystal, and E naught is energy of the same electron, but that electron is of those that electron is of those atom which is not inside the crystal, which is in fact in isolated condition. So E naught represents energy of electron of an isolated atom, and E is energy of the same electron of the atom inside the crystal. Okay, and you can see, since here this potential V dashed of R minus Rj is negative, so definitely the parameters alpha and gamma are positive quantities, and if alpha and gamma are positive, then when you will calculate E, you have to subtract alpha and gamma times this much from E naught. So definitely you can see this E is less than E naught. And how much it is less than E naught? You can easily see that E naught minus E, this will be equal to alpha plus gamma times summation over L e to the power minus I k dot RL. So you can see E naught minus E, this is actually the value of energy by which how much energy of an electron in an atom inside the crystal is less than the electron in isolated atom. And that is simply equal to sum of these two terms. So I have mentioned it here. You can see that this energy is lesser than the energy of the electron in the free atom by a constant factor alpha plus a term which depends on the wave vector k. This is the term which depends on the wave vector k. Actually, this part of the energy, that is gamma times summation over L e to the power minus Ik dot RL, this term actually is responsible for the broadening of the atomic energy level. This is responsible. Okay. So I have mentioned it here that this term of energy broadens the discrete energy, atomic energy levels into the band. Okay, and so you can say that in how the energy band is formed, it is clear that this term appearing in the expression for energy, this is responsible for the formation of energy band. Okay, so you can say this is the last part of this expression which broadens the discrete energy, atomic energy levels into energy bands in the solid. Okay, now we shall apply this result to the explicitly to the 3 cubic type of crystals. In particular case, first of all we consider the case of simple cubic lattice. Okay, you know, in case of simple cubic lattice, this RL, this is the distance of nearest neighbor from the arbitrary origin, and you know this RL is equal to plus minus a comma 0 comma 0, or 0 comma plus minus a comma 0, or 0 0 plus minus a. It means in fact in the present first bracket, this plus minus a represents x and 0 0 represents y and z. In the second bracket, this plus minus a represents y and other represent x and z. Okay, in this way. And so in this condition, what will be the value of this E? In this condition, you can see E will be equal to E naught minus alpha, that will remain at each. Gamma will be also at each. But what will be the value of this? You can see this will be equal to minus 2 gamma times cos kx times A plus cos ky A plus cos kz. And in this condition, the band width is equal to 12 gamma. What is bandwidth? You should remember it. Bandwidth will be 12 gamma. Now, if you will talk about the body-centered cubic lattice, that is B.Sc lattice, in this condition, RL is given as 1 over 2 plus minus A and plus minus A. So, in this condition, again, E is equal to E naught minus alpha will remain at each, and here this will be 8 gamma times cos kx A over 2 times cos ky A over 2 times cos kz over A 2 by 2. Okay, and now see that in this case actually the bandwidth is equal to 16 gamma, and when you talk about the face-centered cubic lattice, that is F.Sc lattice, in that condition this RL is 0 plus minus A comma plus minus A 0 plus minus A plus minus A plus minus A 0, and so E is given as E naught minus alpha minus 4 gamma cos ky A over 2 times cos kz over 8 kz A over 2 plus cos kz A over 2 times cos kx A over 2 plus cos kx A over 2 times cos ky A over 2. Okay, and bandwidth in this for this is 24 gamma. So for simple cubic, what is bandwidth? Bandwidth is 12 gamma. For B.Sc lattice, bandwidth is 16 gamma, and for F.Sc lattice, this is in fact 24 gamma. So you can see the bandwidth in this cubic lattice system is largest for the F.Sc lattice. So in this case actually the overlapping is to more extent. Okay, because we have learned in the first part of the lecture that the width of this band depends on the extent of overlapping. As the overlapping will be larger, the band width will be larger. So you can say that this face-centered cubic system is actually more closely packed with respect to the body-centered and the simple cubic system. Okay. So I think after these two lectures on tight binding approximation, your concept regarding this tight binding method or tight binding approach for the formation of energy bands in solids is now very clear. Okay. So thank you very much.